Okay, this is Fermi Labs. This is Don Lincoln, and I challenge the entire concept of the atomic nucleus being in the standard model, having a huge protons and neutrons and then a couple little electrons. Absolutely not. The entire nucleus is constructed of electrons. But an electron is a strong and a weak force, and the weak force is dark matter. I will show this in exquisite detail because we have actually seen it from experiments. Now, he's going to be asking a bunch of questions, but he wants to know what is smaller than a quark. I can show you what's smaller than a quark. Alright, this is the pulsed red laser, and it's strictly light, so these are photons. They're not nuclear particles, not atomic nucleuses. And that's what CERN does wrong. They started with nucleuses, which is gigantic balls. We started with one little particle. Then we accelerated that one tiny particle. And that one tiny particle, hold on, I got something around here. Here it is. That one tiny particle is literally this structure right here. That's the particle that light is. And it has a dark, and that's the dark matter, literally the dark matter, and you call that the muon neutrino, and this is the electron neutrinos. When this concusses, the muon neutrino walks right away, and the electron neutrino explodes. Exactly what I just showed you in that blue stuff a minute ago, that blue picture. Now, here is the particle accelerating. That's light. Only light. Only light. Only light. This is not nuclear particles. We have accelerated and seen that particle. You just saw it a second ago. It is a box of its electrons. And as it comes forward, they actually split. And then the concussive part walks away. The black balls will walk away from the white. All the way down to here, white only, and then they fuse back in. And here, I will show you that in a second. Here is the particles coming forward out of here. These are the electron showers. I showed you what electron showers look like, and that's exactly what they look like. The black ball does nothing. Here it is right here, and now I'll show you in great detail. You saw it accelerate. We know it's a particle. We know it accelerates. We know it actually separates. That's a black ball. Before it was like this, just exactly before it hit there, I showed you the particle. Then it turns to this. The white comes through here, which they would call that the electron neutrino showers. That's what it is. And then the black balls come back together. So we know they completely, totally separate, absolutely 100%. It's not like they're glued together whatsoever. They're totally separated, and that's what I never could understand. And I always saw it like here, in this. Watch. You see the white on the outside and the black on the inside? I always wonder, why does it do that? The white ones are the concussive, explosive particles. The black ones, they will go to the inside, and the white ones will surround them. This is just the opposite. On concussion, the black ones have to surround the white ones because they're being pushed out somehow. Now, that's what I see. And you can see it. And if you can't see that, I don't know what you're thinking about. And if you don't think it's worth investigating, I don't think you're a true scientist. Right? That's a single slit. These are the interference patterns, and they're not interference. You see that? These are repulsion patterns. These particles do not want to be next to white particles. They push, and that one pushes back, push, 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 push. So they sort of create these lines. Now, most of them are coming through the center of the slit, so they sort of stay together. But you see the black particles coming back together? And the black particles here do not mind being on top of each other. They can be right next to each other, right on top of each other. They have no real interaction with anything. And I believe the only reason we see them is because of the brilliance of the concussion and the radiance of all of the light coming back at us. It sort of obscures it. So there's something there, but it's not absorbing the light. It doesn't do anything. It didn't absorb it and make it do anything. It just sort of got in the way. And it doesn't emit, it doesn't absorb, it doesn't reflect. It just is. The only time we're ever going to see that is because of this interaction and having it walk away from the other particle. And before it did, showing up like this. So this is very, very, very unique. And it's time to look at this and understand it. Right here, we see it accelerate. We see it's a particle. Right there, Einstein's done. And we know there's kind of, and I'm telling you, right in here, there's some energy to harvest here. Because normally when they're together, you've got some energy, but not like this. All right, here's a muon, a neutrino, and an electron neutrino. And it's a black ball and a white ball, and when they come forward and concuss, the black ball just stays the way it is, and the white ball explodes into what they call electron showers. This is what's called Cherenkov radiation, and it is coming through high speed, high voltage, boom, and this is what you get, a nothing and an exploder. That's dark matter. Now, I think I showed this already, but half of a photon is this right here. The black ball is right there, and the explosive part is right here. And they're attached together until they concuss. This is gravity. This wants to get a hold of one of these, just to be with it, hang around with it until it hits something, then it goes away. And here's where it goes. Okay, my friends, it's Roger once again. Fermi Labs is asking if there's something smaller than a quark, and I say absolutely. And that is it right there. Well, actually, this is bigger than a quark. However, at the Venturi, it separates, and here's what happens. That is light from a red pulsed laser. So it's only light. We're starting with the smallest particles there are, light, photons. And then they actually separate into electrons and then into muons and electron neutrinos. Now, here's what happens. This is the nucleus of every atom. So hydrogen has 1,837 electrons because electrons are the only thing that exists. That's the core of a hydrogen. And then it influences one certain zone around it, which relates to one electron, is basically what they say. Now, then you go up from there into, hydrogen has more than one proton in the nucleus sometimes. Hydrogen 2, hydrogen 3. Now, it appears that the protons at 1,837 electrons, when they get into that mass, the Schumann frequency that's vibrating seems to lock it in at a hydrogen atom. Now, it'll go to a little isotope this way, an isotope that way, stable this, stable that, unstable this, unstable that, because there's a bazillion different electrons in between they never took into account. And the only way that any of the chemistry can work, I've determined, is that you have to have all these particles. There's no way one big proton in the center of a hydrogen does all the things it does. It's absolutely silly. Now, this is light. This is light. It's light. So what are we looking at here? We're looking at particles. Now, let's see what they actually look like. Where do you see what they're looking like? So this is the pulse red laser. We're seeing the particle. We're seeing accelerate. So Einstein's done right there. We're seeing it separate from the weak and the strong force. And here's what I'm saying is happening. Every electron, and there's 1,837 of them in a hydrogen, we're looking at just 2 or 4 of them together. All right, that's what these particles look exactly like this. And I show these too, over and over and over, just like that. And when they hit the Venturi, they separate. Now, so don't forget, we're at the smallest particles that exist. Now, here's what happens when it hits the Venturi. See, remember the black particle that was, well, maybe you didn't see that. I'll show you that. Well, let me show it to you now. There's a black particle attached just like this. It's right here, and it hits there, and it explodes. The black ones are just pushed out of the way because they're the dark matter. They don't do anything. They don't absorb, they don't emit, they don't reflect, they don't concuss. They just get out of the way. Now, don't forget what you're just seeing here. And now all the black ones come back in down here, and they do not bother each other. They stay right in with each other. They can mingle each other and don't hurt each other. Now, let me show you something else. All right, remember I told you about the particles? There they are right there. You see the black and the white? Those are nothing more than electrons, side to side, one this way and one that way, which makes them basically neutral, so when they bang into you, they bounce off. When they're in their electron configuration, they will kill you. They will invade you because they want to attach to something. Now, this is right here, is right here. All right, the particles are stacking up on themselves. They're coming through. You really can't see much of the structure. And then they stack up on themselves, and then they hit the venturi. So here we are right here, and bada boom. That's when they hit the venturi, the black and the white separate, which I believe I did show you. But I will show it again, just to be sure that you understand exactly what I'm saying. This was the box of them. All right. And then the blacks can't stay with the white anymore. The white gets sucked through the venturi, causing all kinds of havoc. And the black ones just roll away, out of the way. And the only reason we see them is because of the illumination from behind. They just sort of block out stuff. They don't absorb, they don't attract, they don't do anything. I mean, it's just in the way. It's like a nothing particle, but it has to be there. And we saw it attached to the strong force, the white ball, which is, so there's not a big thing to question here. Well, the thing to question is, why isn't it being taken into consideration? Because if this is the reality of the smallest bits of particles, which it is, we started with light. So we started with the smallest parts. CERN and the rest of them starting with big gigantic photon nucleuses. And then they're digging through all the little bits and pieces. And they're finding some strange looking things, and oh, it's got to be one of these, got to be one of those. Well, I'm showing exactly what it is, and we can absolutely 100%, no question whatsoever, separate that black particle, which has to be the weak force, from the white particle, which has to be the strong force, and then they come back together here. There's no question whatsoever. The only difference between the green and the red is the distance of the concussion. Much longer distance away from the venturi. They start to glow. Same particle. Strong force, weak force. Back to back, it's a photon. Separated, it's an electron. When the electron part, just a half there, separates, it is your boson and fermion, or muon and electron neutrino, however you want to look at it. And when they hit and finally cause the chaos at the right here at the venturi, they're being sucked through. A venturi does that. It makes things accelerate. That's just a fact. It's not something that's disputable. And there's such a concussion of energy that we have increased the energy value here enormously in my mind. And I think there's some way of taking advantage of that, because this was for free. You just have to shine it into a certain construction of a venturi, constructed a certain way, and then you can increase its value. It appears to me. Certainly looks like it to me. All right, this is coming at us, and this is strictly the electron neutrinos. All right, the black balls are coming around the outside, as you saw before. It's not disputable. So these are the particles that are the concussive illuminating particles, and I'm going to show you in a couple other ways. That appears to be a reverse spinner. Everything coming through the venturi was coming from the red laser. So I have to assume that was a red laser particle. And to me, I know there's a right-hand rule. So if it's going to that way, the field spins this way. Now, if it's spinning the wrong way, instead of splaying its field around it like these are, it's gathering its field to within itself. That's what it appears to have done. And then when it concusses with one of these, we see this. And don't forget, now that's coming at us. This is the electron neutrino showers. All right, that's what it is. And the other part, the muon neutrino, is the black ball, and that's outside of this whole envelope of energy. All right, I'm pretty sure that was this particle. I'm not 100% positive. I didn't do these light experiments and pictures. Rod Warren developed this Venturi, and when I saw it, I was just off the wall crazy because I knew what he was doing. And he graciously did all this for, we went on for at least a year or two. Now, anyway, this, and I thank you, Rod, from the deepest part of my heart, my brother, because, what you did is just absolutely phenomenal. Anyway, the particle coming through here is that, I believe, was that white-looking particle that I said could be a reverse spinner. Now, what does that mean? It looks to me like it has some form of a configuration to it. What that means, I don't know. But I see this bleed off, and I see a circular-looking cone being developed. And that's high energy. Every time you see anything bright, it's a higher energy. This is the leading edge because it's coming this way, slamming forward. This is pushing out from this interaction. Now, why? I don't know. What the original? I don't know. Is this related to that? I don't know. Is this related to that? I don't know. I don't know. Is this going to collapse? I don't know. Now let me show you some other pictures of things that relate to this spinning and particles. All right, this is kind of high power stuff, I believe. This is, I believe, the blue laser. And you see when it came through here? I don't know what's going on there. He's got like two little spots, and then up above here, they start to come back into like one little spot, and they're sort of separated down here, whatever that's about. And then you can see these other ones have different characteristics, but they're basically a very similar situation. This is just very, very high power. Why, I don't know. Now, again, right-hand rule, if it's spinning this way, it's going up that way, and it is. It's spinning this way. If it's spinning to the right, it means it's drifting to the left as we take the picture of it. It's spinning and drifting. Now, it's slowing down at the same time. All right, so we know it's going this way, and we know it's spinning to the right because it's drifting to the left. And now it's compressing, so we know it has accelerated and it's slowing down. And this is all through the Venturi. All right, just so you understand, light is a spinning particle. It's a particle, and it has that structure to it like this. And as it spins off this way, and it spins off this way through the slit. And you can see that if you're a machinist, you would fully understand that's a drill bit. And it's spinning this way. And that's why you get these interference patterns. And they're not interference patterns, they're repulsion patterns. The white particle part does not want to be next to each other. So they push the glowy parts apart. And in between, they get the dark strips. And that's just the way it works. They push to shove, push to shove, push to shove, and in between you get the dark strips. Obviously in the center you're getting most of your particles. They're spinning this way and going through that center, going this way, going that way, and so forth. But you can see this circular pattern. That's what light is. This is how light spins. When they say it's a wave, you look at it from this side, yeah, it looks like a wave. It looks like a wave. You can see it going this way and that way. But that's not what's happening. It's a spinning particle. And the faster it spins, the shorter the distance, the shorter the frequency. And the harder it spins, the faster it spins, the harder it hits when it hits you. It's like a drill going faster. If it goes slow, it comes along and just sort of bounces off you a little bit. Alright, check this out. This is outrageous. This is light. Now this is from the red pulse laser. And these are spinning particles. Each one of these, I believe, is a particle. And each one of them, well, I'll show you what they look like in real closeness. Alright, this is how complex this is. And this is light. Okay, as I always say, there's always going to be the dark particle in the center and the light particle on the outside when you have a polar particle. And these particles are all polar because they are literally electrons. Now, they're flowing through here at high speed. Now, I don't know if you can see this or not, because when I'm looking right here, I can't see that. But there is a field that's impressed, and it's so obvious over here when I look into the camera. I don't know if you'll be able to see it or not, but these are just like a whole batch of them coming at once. Now, when we get in real close, you can see these are the particles. I mean, I can't imagine how many freaking particles there are, because every time you see a black and a white, a dark and a white, a dark and a white, a dark and a white, that means that there is a, to me, there's a separation of energy there. And then there's some very interesting looking spots in here that, I mean, there's so much to look at. It's just amazing. These here are very, very interesting to me. Like, and over, even over in here, there's like a double interaction almost, like, I gotta think about that one.